everyone. Welcome to another edition of Astronomy on Tap. Unfortunately, we still have to be virtual, but that doesn't mean that we can still come to your living room from our living room to give you a bit of astronomy. So some of you might already know me. I'm Laila Linke. I'm a PhD student in astronomy at the Argelander Institut for Astronomy. And I just wanted to say hi to you all. Thank you for joining us, and wanted to introduce you to our event today. So in case you haven't already, you can already fill out the virtual Astro quiz that we have. So the link is in the chat. It's also here on the slide next to me, this direction here. You can see the link. Please go there, fill out the quiz, and the answers will be revealed at the end of this event. So maybe you can actually win some prizes there. So we have two great speakers today. We have Konstantinos Migkas and Dr. Robert Reischke, who will talk about two very, very interesting topics. We'll hear a lot about how the universe looks and what it's made of. So yeah, stay tuned for that. Before we start with that, I just wanted to give a quick thanks to our partners. Thanks very much to the SFB Bonn Cologne that supports us also financially, which is really, really nice. Also to the Tai Chi Zentrum in Bonn, who gave a really generous donation. And then we are also still part of the digital science days that are happening during these days and are closing towards the end of November. So yeah, thank you very much. And yeah, finally, you can contact us at any time. You can contact us on all our social media channels. And in particular, you can interact with us in the chat. So here on the side of your screen, you will see the chat. And there we will have Manali and Sandra, who will answer all your questions or relay your questions to the speakers. And you can comment on anything you want and just have a conversation with us. So yeah, with that, I would like to hand over to Maud, who is our moderator for this evening, and who will have a discussion with our first speaker. So take it over, Maud.
Thank you, Laila. Good evening, everyone. Thank you for joining us tonight. So our first speaker, Konstantinos Migkas, is going to talk about a very interesting project he's been working on at the Argelander Institut for Astronomy. And this topic has actually received quite a lot of media coverage. So it's a really hot and interesting topic, especially ESA, NASA, Scientific American, and Forbes talk about this project. So maybe you've already heard of it, but if not, we have him tonight, especially for us, to hear about that very interesting topic. So Konstantinos.
Thank you, Maud, for this kind introduction and for all the advertisement. So I'll share my screen now. Right. So can you see the screen?
Yes.
Okay, great. So please interrupt me if you want, and if you have any questions at any time, it's fine, it's just a discussion. So the question I'm trying to address tonight is, it's quite simple actually, is if the universe looks the same towards every direction, which is something assumed in cosmology, or if we got it all wrong to begin with. So I really want to thank you guys, the Astronomy on Tap team, for organizing this. It's a really nice effort, like to popularize astronomy. So let's start with the basics. So as you may have heard, the universe is believed to have been created with the Big Bang, right? So after the first moments of the Big Bang, it started expanding super fast, rapidly, filling the space with matter and photons. By matter, we mean protons, electrons, and all these particles we've learned about in school. And with radiation, photons, energy. So it kept expanding, and after 14 billion years today, it still expands. So now the question of my research in the PhD and the talk tonight is quite simple. Does this expansion take place at the same rate towards every direction? Or this can be rephrased as, does the same amount of matter exist everywhere in the universe? Or there are certain directions that show some weird behavior, like expanding faster than others, or having more matter, like galaxies or galaxy clusters. So the standard model of cosmology, and specifically the cosmological principle, tells us that the answer to these questions is yes, the universe should expand at the same rate towards every direction, and the matter should be uniform everywhere. But do we actually know that, or we believe that? And the thing is that we don't know that. It's just an assumption that we make. We make this assumption, first of all, because it seems reasonable. It's just a matter of simplicity. And it kind of comes out of math, right? So this cosmological principle thing was introduced in its modern form by Edward Arthur Mill in the 1930s. And Mill said that the universe should appear the same to all observers, no matter where they live in the universe, if they live in our galaxy or in a galaxy far, far away, and every direction should be the same, all the places are the same, etc. However, this was far before we had any observational data in astrophysics to support that, or to test that, actually. So it was most a matter of simplicity, of a philosophical approach, if you want to say that. So the obvious thing to do is to go and test this theory, right? So we can observe the universe in many different ways and in many different frequencies of light. We can do it in radio frequencies, in millimeter, submillimeter, in infrared, in the optical light, the light that we see with our own eyes, in X-rays, and in many other ways. So people have done this actually because it's such a fundamental assumption of the standard cosmological model that we have to be sure if it's true or if it's not true. So the most famous argument for the universe being isotropic, by this we mean that it does behave the same towards every direction, is what we call the cosmic microwave background. So this picture of the universe, think of it like the whole sky. This is a picture of the whole sky. It's so old, it's only 400,000 years after the Big Bang. And you can think of it like this. If the universe is an 80-year-old human, right? 80 years old, like our grandpas, this picture is a picture of this human 20 hours after its birth, right? So it's extremely young. This picture tells us that the universe indeed seems the same towards every direction. You may get confused by this difference in colors, but these are very small fluctuations, actually. So in practice, this looks like extremely similar towards everywhere. So that's the main argument that cosmologists have in favor of what we call isotropy. However, is this actually what we observe when we try to see the cosmic microwave background? The answer is no. What we observe actually is that image on your left of the screen. So there is this huge dipole. So we assume this dipole to be a result of our own movement of our galaxy, like a random movement of our galaxy, within the universe, which is supposed to be isotropic. And after we correct for this movement, because we shouldn't take this into account, we see an extremely uniform result. However, this is just a belief. So we don't know if the whole dipole is because of our movement. It's just something that we assume. And after we assume this, we extract, we delete, we erase this dipole, and we get this isotropy result. Now, the question is this assumption justified? Are we allowed to assume that the whole difference here is because of our own movement? Maybe yes, maybe no. We need independent tests to find out. So people have tested that a lot. For example, a paper of this year actually used observations of galaxies in the infrared wavelengths of more than 3 million galaxies. And they found actually a very strong imbalance in the distribution of these galaxies and quasars, these super energetic black holes, which actually means, in layman's terms, that the universe doesn't look the same towards every direction, like we assumed. And maybe this picture here, the dipole that we saw before, it's not entirely what we assumed it to be up to now. So, does this mean that the cosmological principle is wrong, that the universe is not isotropic? Well, it's not that easy, because there are many studies actually that find isotropy, so finding that the universe is the same everywhere, and many other studies that do not find that and find great differences. So it's very complicated. It's extremely important to find out what's going on, but it's not trivial at all. So who is right? The isotropic guys or the anisotropic guys? So that's where we come in. Since we found out, we came up with this new idea to use our own observations of galaxy clusters and confirm or reject the previous results. So, galaxy clusters, what are these things, right? So, galaxy clusters are these big compilations, let's say, big groups of galaxies, right? So, every galaxy is around 100 billion stars, and every galaxy cluster maybe has some hundreds or thousands of galaxies. They contain, again, around thousands of galaxies. They contain a lot of dark matter, this unknown form of matter in the universe. And they also contain a lot of gas, of plasma, of electrons and protons interacting with each other. In temperatures actually more than 100 million Celsius. So if we see a galaxy cluster in X-rays, we see this thing here, this picture, where we see this emission of all the electrons and protons dancing with each other in the intergalactic medium. If we look at a galaxy cluster with our own eyes, we see this thing here. So we don't see the gas, but we see the galaxies. So depending on what wavelength you look, you'll see something completely different. To get an idea of the size of these things, this line here, so the diameter of a typical galaxy cluster is 6 million light years big. And these small dots, it's just galaxies like our own galaxy. And each galaxy cluster has thousands of them. And we observed more than 300 of these beasts. So that alone is quite fascinating. So the question we are trying to answer is how fast these galaxy clusters are moving away from us, and if this speed is the same towards every direction in the sky. What we found out was that actually they don't seem to go away from us with the same speed. So as you can see in this map here, there is a sky region that the galaxy clusters look like they go away from us slower than other regions. In simple terms, this would mean that the first thing we talked about, the cosmological principles and the isotropy thing, would be wrong, right? Because we see that the expansion of the universe does not look the same towards every direction. So that's my last slide, and I really want to say that people are trying hard to answer what's going on. It's not easy. It doesn't mean that other explanations cannot be the truth behind the results we see and other people see. But we need more analysis. We need more data, more people working on that stuff to answer this very fundamental question about the universe. And a great effort is being done by the eROSITA telescope, a collaboration between Germany and Russia. It's an X-ray telescope that will scan the whole sky for 4 years and will provide us very conclusive answers about this very fundamental question about the universe. So thank you for bearing with me these 5-6 minutes.
Thank you, Kostas. That's really, really interesting. Thank you for the nice talk. So I have a few questions myself. So this anisotropy, you see this difference, could that be due to something else than this cosmological principle? Could the cause of that be something else than something cosmological? Is that possible?
Yes, it is very possible, actually. And that's why we haven't won the Nobel yet, because there are other explanations as well that can play a part of that. For example, there might be something wrong with our observations, right? So in our galaxy, we have a lot of dust and gas running around. So this dust causes X-ray absorption. So when the photons, X-ray photons come to our galaxy, they hit some of this dust and they go away and we cannot observe them. If we don't account for that, we think that the galaxy clusters are going away from us slower or faster. But that's just an artifact of this X-ray absorption. Of course, we correct for that, but no one promises us that there are other things that we don't know yet, and we don't correct for them, that bias our results. The same with the other studies. As a small spoiler, that's probably not the explanation, because we have run many tests on that actually, and we know that's not going on. But there are other explanations as well. For example, in our local universe, and by local we mean some millions or billions of light years, there might be some structures like these superclusters, we call them, clusters of galaxies, that due to gravity they attract us towards them. And if we don't correct for these super large motions, we might misinterpret the velocity with which galaxy clusters and other objects are moving away from us. So this instability might also cause motions like that, and which we might mistake eventually like, a breaking in the law of cosmological principle. So we try to test all that stuff in order to have conclusive answers in the future.
Oh, that's really interesting. And it's nice to see that you are considering all those other possibilities also.
Right.
What would be the consequences for cosmology in case the universe is not isotropic?
So that's a really good question. So the consequences would be large, because our whole model and understanding of the universe is based on that principle. It's based that the universe should be the same towards wherever we look. So if we eventually find out that that's not the case, we have to come up with a new model that takes into account that direction is important after all in the universe, and we have to reconstruct everything. Actually, we have to cause a major paradigm shift. Of course, this is not easy at all, because as we said before, there are many other explanations that might be behind that. So it could take decades until we reach this conclusion, but it would not be the first time. So every cosmological model the humanity ever constructed was wrong up to now. So that's the way that science goes forward, like by contradicting what we know up to now.
Yeah, that's very, very true. So I have another question. You spoke about galaxy clusters. So you're looking at those to deduce this result. How far are they from us? Are they located everywhere, or?
Right. So they are pretty much located everywhere in the universe, but due to our telescopes and their limitations, we can only observe the local ones. So by local, of course, in universe terms, as you very well know, so we mean these huge numbers. So the nearest galaxy cluster to us is around 150 million light years away. And the farthest away from the ones we use is around 5 to 6 billion light years away. So yeah, that's considered local in terms of cosmology, but yeah, that's the distances that we are talking about.
Yeah, that's very, very far.
So just a nice example is that the farthest galaxy cluster in our sample, the light that we observe was emitted when not even the Earth or the Sun were created yet. But now it reaches us and we can observe it with our telescopes in 2020.
Okay, thank you. Do you have any idea how we could get maybe the final answer to this problem, to whether the universe is isotropic or anisotropic?
Right. So what we should do is make the same tests with many different ways, right? So that way, if we find the same result over and over again, we exclude the possibility of what we call systematics, you know, like these faults that might go into our analysis. So what we do now is actually observe galaxy clusters in other wavelengths, like in submillimeter, as you do, for example, in infrared, in other wavelengths. If we keep finding the same behavior for the expansion rate of the universe, no matter in what wavelength we look, this might mean that the phenomenon is cosmological. So repeating independent tests is the way to go.
I see, I see. Wow, that's really, really interesting. Thank you so much for the talk and answering all those questions. So now we will take questions from the chat if there is any. Yeah, if you have any question, don't hesitate to put them in the chat. On YouTube, we have Zandra and Manali who are here to get your question. So don't hesitate. It's really a interesting topic, not so easy, I guess. But yeah, that's.
I think actually the topic is easier than most astrophysical topics for the general public to follow because it's quite simple, right? Does what we see at the sky look the same towards everywhere we look? That's it.
Yeah, that's true. That even looking at the night sky, even without looking at CMB or anything, you can see that it's pretty much the same. Yeah, everywhere we see a lot of stars distributed. Yeah, of course we see the Milky Way, but yeah, that's our own galaxy, so it doesn't count. Yeah, but it's really interesting to see that all the cosmology was based on this cosmological principle, and that today we are able to maybe put that, you know, in on our balance and say, okay, is that really true or not? We really reach like precision cosmology, and that's really nice to be able to ask those big questions.
Exactly. Yes.
So we have a question from the chat actually. So the question is, can you comment on any specific test eROSITA might help with?
Okay. Yeah, sure. So what eROSITA will do is just observe the whole sky for 4 years, right? So at the end, at X-rays, at the end, just imagine was based 3. So with eROSITA, we'll have around 20 times more than that. We'll have thousands of clusters to use at exactly the same way. Actually, around 100,000 galaxy clusters are expected to be observed with eROSITA. We'll make use of a fraction of that, but the statistics will be out of the roof compared to what we do today with eROSITA, and the precision and the accuracy of the observations and everything. So, yeah, it will really provide conclusive answers.
Thank you. That's really nice to hear, especially eROSITA being a German and Russian mission. That's really exciting, of course.
Right, and Bonn actually is heavily related to eROSITA. I mean, for example, in the cluster working group, I think more than 30% of the people come from Bonn and IFA, so that's very encouraging.
That's really, really cool to see. Thank you so much again, Konstantinos, for the talk.
Thank you for having me.
Yeah, thank you. So now we will go on with our second speaker, Robert Reischke. He will talk about a very hot topic. Tonight is really the hot topic of cosmology evening. So he will talk about dark matter, which is always fascinating. So, Robert, whenever you're ready.
Yeah, thank you. Let me share my screen. 1 second. Okay, can you see it well?
Yeah, it works perfectly.
Okay. Let me minimize that. Okay, so yeah, so I'm going to talk about dark matter. As you see here, the scheme of the talk is also a bit Futurama for those of you who know it, and I will continue this scheme throughout this 10 minutes. Okay, so and if there are any questions, just feel free to interrupt me. If something is unclear, just let me know.
Okay.
Maybe just don't ask about the Wittenstalk or so. I don't know that.
Oh, I don't know Futurama, so.
Good, or not, I don't know. Let's see.
Yeah, I guess bad, but yeah.
So let's get cracking. So what is the menu for today? So I just want to, answer two questions. Well, actually, I just want to answer one question, which is, why do we think that dark matter exists? And then I will go to the second question about what is dark matter. And the answer to this is, to say the least, inconclusive. So let's see. Maybe dark matter is, in the end, also the poo of this guy here, which is called Nibbler, but we don't know yet. But you will see this at the end of the talk. So let us start. So why does dark matter actually matter? And for this, we need to go roughly 90 years back to the 1930s, where it was first, let's say, discovered. And it was discovered in the Coma cluster, which you see here in the background. And it was discovered by two people, which is Fritz Zwicky, also known as Mean Zwicky, and Knut Lundmark, in his nice dress here. And how did they do that? So what you see here is you see the Fraunhofer lines, that are the absorption lines in the spectrum of the sun. And if you now imagine the spectrum of the sun, and you imagine the sun is moving away from us, what would happen is that all these lines would move to the right here. So they will get redshifted. If the sun would move towards us very fast, they would go to the left, so they would be blue shifted. So to higher energies for the blue shift and to lower energies for the red shift. And these lines are the absorption lines in the atmosphere of the suns, which are given basically by the elements. So you have the wavelength here, and if you know at which wavelength the sun absorbs, or the elements in the atmosphere of the sun absorbs in the rest frame or in a laboratory frame, then by absorbing how much they shift, you can deduce the velocity of the sun, of any object, right? So this is known as the Doppler effect, and you know this from everyday life. If a car runs by you, the sound when it approaches you and when it's driving away from you is different, right? It is higher and then it goes to lower tones, right? So that's the Doppler effect. And what they used is they used this Doppler effect to estimate the velocities of galaxies in the Coma cluster. And this galaxy clusters, which contains roughly 1,000 galaxies. And what you can then do is you can also ask yourself, okay, how much visible matter is in this galaxy cluster? And you can ask whether this visible matter is heavy enough, or if there's enough matter to hold onto these galaxies if they move with these enormous velocities. And the answer to this question is that there's not enough visible matter to hold these galaxies in place. They should just, over time, they should just dissolve, and this can't work. So this is what they found in the 1930s. Okay, so that's odd. But now you might say, okay, hang on, Robert. Maybe this is like this just in the Coma cluster. So it's like an odd object. Maybe it's the 1930s. They didn't know about all the objects. They didn't see them. So there may be some hidden objects. So there's actually more gravity than was observable by telescopes back then. Well, yes, but if we move forward a few years or a few decades to the 70s, let me introduce you to Vera Rubin, who did a very similar exercise with galaxies and not galaxy clusters. So what she looked at, she again used the redshift information, but what she looked at was this thing here. So what do you see here? So on the x-axis here, you see the radius from the center of a galaxy, and here on the y-axis, you see the amount of circular motion of stars and gas in this galaxy. And what you expect, if only the visible matter is there, is this dashed line here, which is labeled disk. But what you observe is actually this here, these data points. So, and this is only possible if you have, again, much more matter there than you see, right? So this is another confirmation. So we've seen it on the scales of galaxy clusters, and we've seen it on the scales of galaxies, right?
Okay, so
Yeah.
we think that there is this dark matter because we see more velocity than we should in those galaxies. But are we maybe observing some galaxies without this effect or without any missing matter in them? Does that exist or?
Yeah, so that's a good question. So you might, for example, also say that. So let me go back a bit. So you might also say, okay, maybe we just don't understand gravity, right? But then, so if we don't understand gravity, then we would expect something like this in every galaxy to happen. But there are actually galaxies observed which have the same amount of visible and what we would call gravitating matter, or their mass to light ratio, as it is called, is roughly 1, right? And this basically tells you that you can have some processes which, or it's a dynamic process, right? It's nothing which is inherent to gravity we just don't understand it on these scales, right? So
Okay.
this exists, yeah. Okay. So again, recapping, we know it for galaxy clusters, or for the Coma cluster in this case. Today we know it for other galaxy clusters, and we know it for galaxies, that in most galaxies you just see much higher velocities than you would expect to see when there was no dark matter, right? Or no matter which is not interacting with photons. Good. So now the question is, so we have looked at galaxies in our neighborhood, and we have looked at the Coma cluster. And now the question is this actually a consistent picture through cosmic time? So is dark matter a consistent picture through cosmic time? Because we've just heard in the previous talk that the universe is quite old, and we also had this picture of the cosmic microwave background, right? Where we just learned, okay, it was released 20 hours in a 80-year-old human being's life, or a few 100,000 years after the Big Bang. So this is again this picture of the satellite and of the Planck satellite, of the cosmic microwave background and of the fluctuations in the temperature. And the question is, now if you have these fluctuations, so these fluctuations trace the the amount of matter back then, and now if you act with gravity on this, you should end up today at the structure you see today. So what you see is a picture from the Sloan Digital Sky Survey, and this is how the universe looks like today. So what should happen is, okay, you have these fluctuations. Now gravity acts, and the fluctuations, so overdensities become more overdense, and underdensities become more underdense. Good. So this should work, but it turns out it doesn't. And the answer is that in order to produce the structures we see today, we would need much more structure in the cosmic microwave background. And since the cosmic microwave background is basically produced by photons, you can also conclude from this that if you have some kind of matter which does not couple with photons, you can have much more structure in the cosmic microwave background without or you can have much more structure early on without it showing up in the cosmic microwave background, and then this still works. So we have now a lot of evidence for dark matter. We have it on galactic scales, on galaxy cluster scales, and on scales of, well, the observable universe, basically, and at different times.
Okay. That's pretty amazing. I have a question. We have a question from the chat about the evidence for dark matter at the galaxy and galaxy cluster scale. Someone is asking, would it be a fair summary to say that some galaxies are spinning faster than expected from the visible matter only?
So for disk galaxies, you could say that the stars in the disk and the gas in the disk is moving faster than you would expect. Yes. For galaxy clusters, you more have a random motion in the potential well, and if with the speed they are moving, you would expect that they just move out of the potential well because they have enough kinetic energy to escape the potential well, like a rocket escaping the potential well of the Earth, right? Yeah.
Okay.
But yeah,
okay.
you could say this. Yeah. So, yeah.
Thank you.
Okay. So now, moving to the second question, what is dark matter? So this is going to be a bit shorter or not, let's see. But the short answer is we don't know yet. And on the bright side, to some degree at least, we have a lot of ideas what dark matter could be. So again, at the moment, we just know dark matter exists on cosmological scales. But we don't know what it is from a particle physics view, right? So dark matter does not fit into what we call the standard model of particle physics. But let me show you a few ideas which I borrowed from XKCD. So what is shown here? So you have here on this line, you have mass ranges, right? So you have here, which is called microelectron volt, which is very, very light, right? So you have here, for example, at an electron weighs roughly 500 kiloelectron volts, and in kilograms, this is like around 10 to the minus 30 kilograms, plus minus. Then you have here micrograms, milligrams, grams, you have kilograms, tons, and then you go up here all the scale, blah, blah, blah. 10 to the 30 kilograms is roughly the mass of the sun. And we have, what is shown here is a lot of candidates for dark matter. And yeah, so a few of them are serious candidates, a few of them are joke candidates. Let's see if we can spot them.
Yeah, I see, for example, pollen. I'm really allergic to it. So I hope dark matter is not made of pollen. Otherwise, that would be really bad for a lot of humans like me.
Yeah, exactly. Because humans like you then think that the whole universe is made out of pollen, like with dark matter.
Yeah. In spring, that's pretty much, that's close to the reality, I would say.
Yeah.
That's really interesting. Most of those candidates I do not know. And actually, I would like to ask you a question about one of those, because I've seen it in the literature quite a lot of times. So I guess it's popular, probably one of the most popular one. It's axions.
Mm-hmm.
I've heard of them a lot, but I don't know what they are.
Okay, so let me first say that the scale here to the left could go on further to the left. So they could be much lighter. But what are axions? So, or why are they so popular? So axions are, well, a light dark matter candidate, and they are so popular because they were actually invented. So they were invented to solve a problem which occurs in particle physics, which occurs in quantum chromodynamics, which describes the interaction of quarks, basically quarks and gluons, right? And
okay.
And so they are motivated for this because if there's a problem in QCD, because you would expect that there's a dipole moment for certain particles, and you don't observe it. And the axion is basically introduced to make this dipole moment vanish. And for which is called the QCD axion, it has a very particular mass, right? So which is around this thing. But another interesting thing about axions is that as a dark matter candidate, they can be very light. They can be much, much, much lighter than this. And as some of you might have heard, that you can assign each particle also a wave character, right? So there's this wave particle duality from quantum mechanics. And if the particle is lighter, or as lighter as the particle is, as larger is its wavelength, right? And if the wavelength, if you can probe, or if you see the wave nature of the particle, then you can see quantum effects basically, or interference effects. And the axions can actually be so light that this wavelength, which is called de Broglie wavelength, could be of the order of galaxies, or the size of galaxies. And then you would see quantum effects from this kind of dark matter on galaxies. And this is one way to rule out this, or to constrain this picture here from the left-hand side, because if they are too light, you would see observable effects in the pattern of galaxy clustering, for example, how galaxies cluster in the universe. Yeah.
Okay, I see. That's really interesting to see such a small and light candidate explain such a huge missing mass in the universe. That's really, really interesting. Robert, we also have another question from the chat.
Mm-hmm.
Someone is asking if this phenomena, so I guess dark matter, could not be explained by the fact that gravity may work differently than we currently think.
Yeah, so this is what I addressed in a bit before. So the problem there is that if this is the case, right, then you would expect that gravity works a different way everywhere. So what we can, for example, do is we can, for example, do tests on Earth, right? So, and on Earth, gravity is very well tested also in the solar system. What you have to do is basically you have to do a change in the strength of gravity. So gravity has to be much, much stronger than what you would expect, right? So you measure mass to light ratios, or missing matter, which is a factor of 100. So gravity should be 100 times stronger on certain scales than what we have observed. And the problem with this is that this does not fit all the observations, because as I showed you, we have observations on galactic scales, on galaxy cluster scales, which is even larger, and on the cosmic microwave background. And all models with modifications to gravity, which are consistent with observations, still need dark matter. So yeah, this was an idea and the motivation for modified gravity, but it doesn't work as far as we know.
Okay. That's really interesting to see that this was also taken into account, and that we now have a better idea whether that could be an explanation or not. Sorry, Robert, it's really, the topic is so hot. We again have another question from the chat for you. So this question is, how will the ELT telescope bring new knowledge about dark matter in a few years? Do you have any idea about that?
Oh, that's a good question. So it's good that we are back at this plot, right? So what the ELT can, for example, do is that it can rule out more stuff on the right of this plot, for example, right? Because it can have very good resolution, or very high angular resolution on objects. So you can rule out more objects on the right side of this plot. Or on this picture, right? So because when objects are, so these objects are, let's say, are quite heavy, right? On this side, and if you can, so if they are so heavy, you would expect some astronomical consequences, which they should have when they have a certain mass. And the higher the resolution of a telescope is, the smaller objects you can basically resolve in certain systems, and the disturbance they put on these systems. So this is one way where it would certainly help. On the other hand, from the left side, you mostly come with, you can also do things like that on the left side, but you also come from a, let's say, large cosmological observations of the structure of the universe. Yeah.
Thank you for the explanation. Yeah.
Okay, good. So maybe I go back to the slide if there are more questions at some point, but okay, so let me just finish with my summary. So if you want to take something home from this, right? So first, we have an overwhelming evidence for dark matter, right? So it's on different scales at different times in the universe. We know it on galactic scales. We know it on cluster scales. We know it on the scale of the cosmic microwave background, which is kind of the largest thing we observe in the universe, the largest structure, if you want. And there's other evidence which I haven't shown you because of lack of time. As I answered in one question, dark matter cannot be explained by modifications to gravity, at least not alone, right? So with all modified gravity models, you still need dark matter if you want to fit all the observations. But at the same time, dark matter does not yet fit into our model of particle physics, and we don't know what kind of particle it is. There are numerous experiments to test this. There's xenon 1 ton, there's the ice cube experiment in the South Pole, and so on and so on and so on. And there's the LHC, of course, but so far nothing has been found. So the only possibility is that we have to stay curious and move forward. And with this, I close my talk and take more questions if there are.
Thank you so much for the very interesting talk and this complete explanation of dark matter. I have only one last question, and then I think we would wrap it up. There is so many questions about dark matter. It's really mysterious. Is there anything certain about dark matter?
Okay, so that's an interesting question. So it's dark. That is quite certain. So if it interacts with photons, it does it only very, very weakly. So this is something we know from the observations. What else do we know? We know that if dark matter is a particle, it should be stable over the age of the universe. Right? If it's not stable, then there wouldn't be any dark matter. These are two things we really know. Another thing we know is that it's very close to what we call collisionless, right? So that it's just basically how you can imagine this, that it behaves like just a collection of sand grains, and it doesn't behave exactly like a fluid, for example, right? It's just more like a collection of sand grains. So this is what we mean with collisionless. So they don't collide very often. So these are the things which we know, which are certain of dark matter. As you've seen in the picture, there are certain ranges which are excluded already from observations, and we are narrowing down this more and more by observations. But from the properties, which are really where we are sure, these are basically the three key properties, and this makes it hard to find as well. For example, if you look at the Large Hadron Collider for dark matter, and you find something, but you find it, how you look for it is it goes through the detector, and then you have some missing energy because you don't detect it. But you can't tell whether it decays when it's outside of the detector. So what about the lifespan? You can't probe it with at the LHC. You need something different there. But so these are current questions here.
Yeah, Yeah, at the particle level, we are really entering precision that is just madness, not even something we can conceive almost on our human brain. That's really, really interesting. Thank you so much again, Robert, for the very nice talk, and thank you everyone for all the questions. We will now go on with the quiz. We have Sven that will give you the answer of the quiz.
Yes. Hello, everyone. I hope you can hear me and see my screen. Yeah, welcome to the November virtual quiz. I hope you have all sent in your answers because we will stop accepting replies by now. And yeah, let us go through the questions one by one. So the first question was in the Astronews field. And we asked you that, well, basically, which technology will enable us to prevent or mitigate wildfires caused by lightning? A technology that is named after Star Trek. And the correct answer to that is a tractor beam. So how does a tractor beam work? In Star Trek, to be honest, I cannot explain it to you. And if I could, then I would first collect my Nobel Prize before explaining it to you. But how it works here is the following. We have basically little particles in the air that we heat with a laser. And these heated particles, of course, heat the air around it. And lightning prefers hot air over cold air to strike, basically. So with this laser, you can basically carve a path for the lightning to strike. And you can see that here in this little video. You see here, this is the laser beam that is lighting up these particles. And now you see the first lightning struck exactly where the beam was. The others are now random. They have nothing to do with that. So in principle, this technology works. Of course, we need to be able to apply it to a bit larger scale than to metal plates. But yeah, we might soon be able to direct lightning strikes with tractor beams, which sounds pretty futuristic, I think. So the second Astronews question is, whenever there are 2 full moons in 1 month, as happened this year on Halloween, this moon is called, and the answer to that is that it's called a blue moon. This has nothing to do with the moon being blue or anything. The second full moon in a month is not bluer than the first or anything. And yeah, interesting fun fact, whenever there is a full moon after the 28th of a month, so especially on Halloween, it is always a blue moon. So yeah, we have this nice picture here. Okay, for the last question of the Astronews, we have had a 7-month-long radio silence with a probe, and now we have re-established contact. And this spacecraft is the Voyager 2. Voyager 2 is, well, one of the furthest away probes from Earth. It has, yeah, depending on who you ask, left the influence of the sun, the sphere of influence of the sun. So it's really, really far away, and NASA had to do some repairs on their deep space network that allows it to communicate with probes that are in deep space. So they had to shut it off basically for 7 months. And after that, they were able to re-establish contact, which is by no means a trivial task, because this Voyager probe weighs, well, a few tons, and it's literally millions upon millions of kilometers away. And to be able to send signals there and receive them back is, yeah. Moving on to the Pictionary, where we had talented astronomers draw pictures, and you had to guess the pictures. So the first one is quite obviously a star, and you have spots on them, and so yeah, these spots are called sunspots. They are spots that have a bit lower temperature than the rest of the surface of the sun. We have this 11-year solar cycle that is characterized by the number of sunspots that you observe over a given period of time. And this correlates also with the amount of solar flares and so on and so forth. Right now we're at a solar minimum, so the solar activity will increase now, so we can expect solar flares, more polar lights, and well, maybe some power outages due to solar flares. Our second Pictionary, also drawn by a talented astronomer, which, well, the sketch is a bit more crude, but the probe or the station is still, in my opinion, very recognizable, which is the ISS. And yeah, I in my opinion, especially this array of solar panels is just very, very characteristic. Whenever I see that, I immediately think of the ISS, and I hope many of you do too. The third one was, in my opinion, the most difficult one. Maybe some people that have more ideas about history of spaceflight disagree, but this is the Apollo-Soyuz test project. It's officially marks, or many people believe that this marks the end of the space race. It's the first manned mission where the Soviet Union and the US were cooperating. An Apollo probe and the Soyuz probe were docking, and the astronauts shook hands through the ledge. So this was a very, very important mission, not for the science that was gained, but more for the diplomacy. Okay, with that, we move on to our last category, movie posters, where we present you very, very minimalistic movie posters, and you have to guess the movie that they are about. So the first one is just a man jumping on a cable, and that is the movie GoldenEye, the famous James Bond movie. And with that movie, unfortunately, there comes very, very sad news, namely that this telescope, the Arecibo telescope, that was the one of the filming locations for this movie. It was a dish where signals were sent to the GoldenEye satellite. Unfortunately, it has been decommissioned now because there's some cable ruptured and it damaged the dish, as you can see here. And the people deemed, or the people responsible said it's too risky to try to build this up. Probably people will get hurt and more buildings will get destroyed. So they decided to shut it down, decommission it, and start deconstructing it, which is very, very sad, since this telescope has played a big role in basically all aspects of radio astronomy, especially also in SETI, in the search for extraterrestrial intelligence. Even some military operations were conducted with this. For example, this telescope was able to locate Soviet radar by the signatures that bounced off the moon. So it was an extremely powerful telescope that now, unfortunately, will not be conducting science operations anymore. Then the second one, well, the movie is the Armageddon, which you can see from this nice space shuttle flying to this big rock. Scientifically, this movie has a few problems, but I'm sure most of you that have seen it have recognized it from the sketch, because it's a very characteristic scene with the space shuttles flying towards this asteroid. And the last movie, just some astronaut hanging on a very, very long tether, was supposed to describe the movie Gravity, which I'm sure many of you have seen as well. Science-wise, it's definitely much, much better than Armageddon. It is a bit wacky on the details, but it depicts a very, very real problem, namely the Kessler syndrome, which basically is, well, it hasn't happened yet, but it is a real danger that when one satellite is hit by debris, this satellite will be destroyed and create more debris. This more debris will destroy more satellites, which will in turn become even more debris and will destroy even more satellites. So as soon as we have enough satellites in orbit, this could lead to a chain reaction that destroys all the objects we have in orbit and might make space travel for the next 100 to 500 years very, very hard. So this problem is an actual problem that we might be steering towards, and that we have to be careful that this does not happen, because that would mean very, very many bad things for us. With that, let us come to the prizes, or first, how to win the prizes. You win the prizes if you have more than half the answers correct, and then you just have to be lucky enough to be drawn as one of the winners. And you have to put a valid email address in the form, otherwise we cannot contact you. And voila, you have already won. So what can you win today? You can win again a metal figurine, this time of the Voyager spacecraft that we have now luckily established contact with again. You can win a thermal mug for coffee from Astronomy on Tap with our logo, of which we can see a nice sketch here. And you can win one of those two books. You can choose either English or German. And you can win a sporty voucher for Tai Chi in Bonn. So don't take this if you don't live in Bonn. This cannot be used in other cities. But yeah. With that, I thank you all for participating in the quiz. I hope you win, and I mean you personally, not all the others that are watching. And I hope to see you next month. Bye.
I think I just realized that no one could hear me, but thanks again for reminding me that I actually have to unmute before you can hear me. So, hi everyone. I wanted to say a big thank you to all our speakers, a big thank you to Sven, a big thank you to our quizmaster, and I wanted to thank all the audience for being with us, for listening to the talks, and I hope you learned as much as I did, because I learned a lot. Just a reminder, you can actually contact us at any time on all our social media. You can follow our YouTube channel here, so you get reminded the next time we are on. And of course, you can send us an email. But the most important thing is you can join our next AOT that is happening in December. So it will not be on the last Tuesday, because the last Tuesday will collide with all the holidays happening there. So we will be on the 15th of December, same time, same place here on YouTube, unfortunately. There will be a quiz, there will be prizes again. So if you are unlucky and don't win this time, you can win the next time. Just be sure to participate in the quiz. And we will have two amazing talks. We have one speaker from the University of Oslo who will talk about noctilucent clouds. So if you're interested in that, and even if you don't have any idea what it is, it's really fascinating. I'm sure we will see a lot of really pretty pictures there. And we will also have a talk by Dr. Abel Schotemeyer, who is from the Argelander Institut of Astronomy here in Bonn. And yeah, I really hope to see you there. And yeah, have a good night and see you then.